Okay, and we'll get started in like 1 more minute. At 2:16 we'll start. We'll just wait for a few more people to join. Okay, let's get started. First, I'll give a quick introduction of myself. Hi, I am Vivek. I'm a first-year master's student in computer science. My research focus is mainly into machine learning. Prior coming to UC Davis, I worked as a solutions architect at a fintech firm in India. There I've built numerous number of big data and analytics products. Then I thought, I have to learn more, and I should go deeper into the research. So that's when I chose to come and do masters in here. I will share my GitHub profile and other details in a chat or in the announcement section of Canvas. Feel free to connect. I'll be pretty open, so I'll try to be pretty open. So always feel free to communicate whatever problems that you have. Now, today I was supposed to discuss about logistic regression and feed-forward neural networks. So, there is the classical way of, taking this discussion session so far has been like, we take a problem and we try to, do it as fast as we can. But in my terminology, what I feel the best way to learn is you define a problem statement in the start, and then by trying to solve that problem, if you learn, that would be the best learning practice, is what I believe in. So for learning these concepts also, we're going to follow the similar kind of learning strategy. First, we'll define a problem, and then we'll try to understand the concepts in detail. So the idea is, while trying to learn the solution, we'll also learn the concepts, right? So for logistic regression today, what we're going to do is we're going to take a very interesting data set. It's called Titanic dataset. I'll also use the board. Sometimes if something is not clear, do let me know. So is the board visible? Whatever I'm writing, is it visible? It's good?
Yeah, it's visible.
Yeah, good. Awesome. Okay. So let me define the problem first, so that you all understand it, what we are trying to do by end of this segment. So everybody, I think, knows the Titanic story. What happened is a lot of people in the whoever boarded the ship, many people survived and many people are dead. And each person have different attributes, right? So what we are trying to figure out is, based upon different attributes, in the sense there is age, there is there is age, and there is gender. There are many categories, many features on which we can define a person who has boarded the Titanic. He might be in the first class, he might be in the second class. Like this, there are many many columns or many features, many attributes to every person that's boarded Titanic. Now, what problem we are trying to solve today is, we are trying to figure out, based on these attributes, if a person will survive or not. Now, that is the question that we're trying to answer. Long story short, to simplify even it better, if I am a person today, if I board a first class Titanic, with my age is around 24. So if I board Titanic, I wanted to know if I will survive or not. So that is what we're trying to figure out. Now, if you see this problem, it is a classification problem. It's not a traditional linear regression problem that you have learned already, right? So if we take the survival as 1 and not survival as 0, there in your prediction column there will only be two values. One is survived, that is like 1. One is not survival, that is 0. So how do we model it in a mathematical way so that we figure out an equation which can give us whether a person will survive or not? In previous classes by now, I think oh, there are some questions in chat. Oh, is it? Yes, yeah, awesome. In previous sessions, you have learned I think polynomial regression already. If I wanted to summarize polynomial regression in like a simple manner, whatever. Let's say y is what we are trying to predict, and x is the input vector. This x is the input vector. X is nothing but your features. What we are trying to, and there are set of points. Now, based upon these points, and however the distribution is there with respect to x, we're trying to fit a line through it. That is what we are trying to do in polynomial regression. But can we use polynomial regression for a logistic problem? Like, can we? Let's see if we can, right? So if we take the data set, let's assume there is only one input feature, that is nothing but age. And this is, let's say this is my x, right? And let y be my survival class. It can be either 0 or 1. So let's say this is survival. It can take values either 0 or 1. Now, as I said, x is an age. Let's say I'm plotting age as from 0 to, let's say, 80. If I remember it correctly, in the movie, around all the aged people, I think, get to board the the ships which the smaller ships, right? So like my assumption in general is whoever has higher age, whoever has higher age get to board that ship first. So let's say these are the data points. These are the points. Let's say this is some 35, and this guy survived, and this is some 48, and this lady also survived. Whoever it is, it's and let's say there are people who are less than 20, and let's say most of them didn't survive. Now, if we now this clearly looks like just a XY plane, and if we try to put a line for this data, let's say we by somehow we are able to figure out this line. Let's say this line we are calling it as theta transpose x, right? Now, if we see this data, what can we understand? Whatever points that are below this line, I can classify them as 1, right? And whatever points that are above this line, I can classify them as 0. So far so good, right? So if I use this classification problem, if I use linear regression, whatever you studied for doing a classification, it looks like it's working. But the problem with this method is there will be a lot of outliers in the data set, right? Now, there is a possibility where, let's say there are children. Children's age is somewhere around, let's say, 5 years. And we know that they survive. Now, immediately what happens because of these few outliers that we have, the entire line gets shifted like this, let's say. Now, is it a good thing to use linear regression for this kind of problems? No, because even small outliers like this is affecting the overall model in a larger run. So long story short, we cannot use linear regression for classification problem. So what do we do? So what should you do? When computer scientists were posed with this problem, they were thinking about what are the things that they should do. One thing what we want is we need a function which will take the value x and which will input the values between 0 and 1. That's all we want, because it's a binary classification problem that we're trying to solve, and we want a function that can release 0 and 1, right? Turns out there is a beautiful function called sigmoid of x. If I define sigmoid of z, it is 1 by 1 plus e power minus z, right? This is actually a very beautiful function. If you plot it, this function, from negative infinity till this point, and this is 0, until positive infinity, now if at all the value of z is greater than 0, then it'll always be greater than 0.5. And if at all the value is less than 0, the value is always less than 0.5. Now, this is a very interesting thing for us, right? Previously, we are not able to get a clear decision boundary. But instead of plugging in just the linear combination and trying to fit the data to it, what if we fit this data to this function? What if I make this sigmoid as my hypothesis function? Apparently, when you take the log likelihood estimation and you figure out the theta, I think that's what we have done in the class. You get a nice bell curve like this, and we do the gradient descent for finding out thetas. This is not a bad approximation. This is like a really good function that could solve our classification problem. So what we do is, instead of this z, we'll just take the theta transpose x and we plug it in. By using maximum likelihood estimation, and we try to figure out what are the values of theta. So this is how logistic regression works in a very simple manner. I could go in details of math and tell you, how this theta transpose x, how this thetas are being found, but that will take too much time, and we don't have that much time. So for that, I think you guys can come to my office hours. I'll be able to explain it there much more clearly. But the whole idea, what I want you guys to take out is, instead of in linear regression, because we are getting a problem even with a slight deviation from our even from slight deviation of the data is giving us a lot of problems. So we use this function called sigmoid, which is helping us set the decision boundary in a very clear manner. Any questions so far? Or is my pace too fast, or anything? Any questions so far? Good so far. Yeah, awesome. Now let's see the Titanic problem, right? Very interesting problem. Okay. So not just this Titanic problem that you're trying to solve, any machine learning problem that you'll ever see will have certain steps. Uh, it may be, NLP, computer vision. It can be, generating reinforcement learning. Playing AlphaGo. All of these things. There are certain steps that these things will follow, right? In a machine learning thing, in any machine learning problem. So if I list out what are the steps that are involved in solving, if I aggregate into a higher level and put it into a neat fashion, so there are 5 major steps. First one is data exploration. Second one is pre-processing and feature selection. Third step is training. Fourth step is testing. And fifth step is post-processing. So you can break down any machine learning problem into these 5 steps, right? Now, if I just talk about all these, one by one, I could go on for like an hour. But what we are here is to learn how to, do it in a code format. That's what we'll do in a hands-on. But a rough idea of what each step means is data exploration is essentially when you are given the initial data set. We'll try to explore, we try to find some insights as a domain expert. What are all the things, like how is the data distributed, what are the kind of features that are there, what are the parameters, whether they are numerical attributes or categorical attributes. We'll try to figure out all those things in the data exploration step. And in the pre-processing step and feature selection, for the problem that is given for us, we'll have to choose the certain values, certain attributes that can get my output in a very good manner. For choosing those, for example, in our case, in Titanic case, the features that we may choose can be age, can be gender, can be class. It can be any of these values. So what are all the features that we need to choose? That all thing comes under the feature selection part. And similarly, pre-processing is like if at all we have numerical values, the computer cannot understand strings or any other thing. So we have to convert everything into a format that it understands, into ones and zeros. So what are the pre-processing steps involved and why? So that is what pre-processing means. And then comes the actual training. So in training, we'll have to figure out, what is the model that we're going to use, and what is the solver, what is the optimization technique that we will use? Is it like SGD? Is it something else? That all comes in the training phase. And in testing, we'll have to see like how my whole overall model after training is performing. And last step, post processing, it might not be valid for this particular use case, but in many computer vision or NLP problems, this is a very crucial step where the outputs of your neural network, you have to it's not directly consumable. So to convert into a consumable format, you have to do some post processing. One thing that I'll say here, ensure that you get all of these in your brain, like it should be implanted. So if not, you probably will flunk the class. So ensure you understand what each of these things mean. Any questions so far? Is it all clear? Am I going too fast? Any questions? Yeah, you can use the chat and say yes or no, but yeah, I understand how these things go. Okay, so enough of talk. Let's actually get into the coding part. Oh, okay. Okay. Good morning, everyone. Last time in the last discussion, I said I'll upload some supplemental material, but due to some time constraints, I wasn't able to do so. But here I am explaining about some things. I know I said in the last discussion that I will go through the program step by step rather than reading out from Jupyter Notebook. But unfortunately, this quarter is we have very less time for discussions, and I can't afford to take full-blown coding session from scratch. So here I am back with the Jupyter Notebook, and I'll try to explain the logistic regression part again. And we'll also cover feed-forward neural networks and Newton's method as well. So if you remember in the last discussion, we were trying to look at Titanic dataset and trying to predict, given certain attributes, whether whoever is there in the Titanic will be, sorry, whoever is there on the Titanic, will they be survived or not? So let's just go through the Jupyter Notebook quickly till whatever we have covered. So starting with, we are doing some imports. Like these are all the standard libraries that we use. We are using pandas, numpy, matplotlib, and seaborn SNS. The first two are for data processing, pandas and numpy, and the next two are for the plots. So in the second step, what we are trying to do is we are taking the CSV file, whichever is already there, and we are going and putting it in a Titanic data frame. So here you can see these are all the columns that we have, and passengers, passenger ID, survived, P class, name. These are all the features that are there for this particular data set. And what we are trying to do is we are trying to based upon all the features that are available, we are just trying to figure out if someone is survived or not. And what we'll also do is we'll try to predict, if given some features, will they be able to survive or not. So that is what we are trying to do. Now, moving forward, as I said in the previous class, there are four major steps, 4 or 5 major steps in the entire machine learning pipeline. We started with the exploratory data analysis. Most of the time, like rather than the actual machine learning problem, getting the data into a right shape would take more time than training your model. So I thought it would be a good time to spend different. It's a good time to explore different methods of exploring the data. So I feel one of the best ways to explore data is using plots. So we use different plots to explore the data that we have. So we have count. I will talk about count plot, heat map, histogram, and box plot. So first, let's see how we can use count plot to get some insights about our data. First, we are taking count plot to see how many of people have survived and how many have not survived. So to see the balance between the labels that we have. So here we can see there are around 300 people who survived, and there are around 500 people who didn't survive. So this basically uses an idea that we have both positive labels and negative labels in somewhat equivalent manner, like 60-40. So in general, in machine learning problems, that defines a good data set. So it is okay for us. Now, the next insight that we would like to know is based upon other features, how the data is being distributed, right? So now let's say if we take sex as the parameter, and we gender as a parameter, and we try to plot it around the count plot. Let's see how that distribution is looking like. So here also we can see how the distribution is in between male and female, and how the survival rate is there on the how the survival rate is amongst the passengers. So here we can see out of whoever have survived, uh, like majority of them are female, if I remember the story correctly. So first priority is always given to women and children. So the data also speaks the same. uh, Very interesting plots. But we can also do the same thing with passenger class and see some and get some insight into the data using the same count plot. Here also you can see there are three passenger classes. So again, it says the same thing. If at all you're in the first class, the probability of survival is more, and if at all you're in third class, the probability of you surviving is very less, as indicated by the data we have. And if we take now we have to see, are there any nulls in the entire data set? So we'll use heat map. This is not always a straightforward intuitive manner to explore the data set, but this is a very good visualization which can show us whether is a very good data set which will show us how many nulls are there in the data. So here we can see the age column have too many null values, and also the cabin values are also have too many null values. Let's just go forward and see and plot the histogram of how many nulls are there. Okay, so now the next thing that we're doing is we're trying to see how the distribution of age is there in the entire data set. So here we can see, first thing what we're doing is we're just dropping all the null values so that it doesn't affect how the distribution is there. And here you can see it is more or less following data distribution of normal. It's like a uniformly distributed around the mean 30. So majority of the people on the Titanic are around age 30. That's what we can understand. One thing that you can observe from here is till before we were just trying to look at the categorical variables of the data, but from here we are looking at the numerical variables and how the distribution is looking like. And if we also plot the second histogram, so here also we see there are fare details, like how the fare is distributed. And there is one more plot which we can do using box plot, which can tell us the mean age of people in a particular in a particular class. So here we're using box plot. Now here we can clearly say if at all they are in first class, so their age is in between 28 to 50, majority of them. So that's what it is trying to say. And if at all they're in third class, it's between 20 to 30. That is what the data is speaking here. Now, these are some different types of plots that we can use to understand the data in better manner. So far there are some insights we are able to draw from here, like how many people have survived with respect to gender, with respect to the passenger class, and how the age distribution is there, how the fare distribution is there, and how the age is distributed with passenger class. All these kinds of understanding that we get. Usually what is the right way to actually do now the next step usually is to select what the features what features are right for this particular data set. In polynomial regression, you might have seen methods like covariance plots, where you try to understand how one variable is affecting the prediction class, and then you'll try to figure out based on that which features to select. But here it's a logistic regression problem. It's the output variables are categorical, not a it's not a continuous variable. It's a discrete variable. So we cannot use that covariance matrix directly in here. There is another way to do how other way to find out how the output values are correlated with the input features, but we won't discuss about it right now. It's called principal PCA. We'll learn it towards the end of the quarter. As of now, we are going to take all the features that are available for us and train a model. Now, as I said, in the data process, in the machine learning pipeline, then the second step is pre-processing. So for pre-processing, we are there are multiple ways, there are multiple techniques in the pre-processing segment. First thing, as we have seen in the previous place, there are a lot of nulls in the age column. So we need to somehow figure out a method to fill all the null values. So we'll learn about how to use functions to fill these null values and how to create new columns in pandas, and how to do one-hot encoding, and how to train and test, how to split the data into training and testing set. So coming to the first thing, as I said, we have to create in the age column, as you have seen in the above segment. In the age, there are a lot of null values. So how do we fill these null values? So here you can see I'm recreating the age column. So this is how you usually create new columns in pandas data frame. So we are recreating the age column, and we are sending the existing age column and passenger class into the function, and we are applying the impute missing age function to the age and p class. So essentially what will happen is, for each row item in the data frame, for each age and p class in the data frame that we have, it will go into this function, and it will figure out what would be the right age for that, and it will return that age here. So that's what here apply this function means. So so let me just talk about the function that we are using here. We are using an impute missing age function. So it is basically taking it's a list of the first value of the list is nothing but the age, and the second value in the list is nothing but the passenger class. Now age equals to the column 0. That's what we are saying, and the passenger class will be the first index value in the list of the columns. And first of all, we are checking whether the age is null or not. If at all the age is null, then we don't have to do anything. Sorry, if at all the age is not null, we don't have to do anything, just return the age. If the age is null, then we are basically taking the mean age with that p class and just returning. I think we have already seen here from this box plot how the age is distributed across different categories, and one or the other way we know that the mean age is somewhere around 35, and if we fill all the blank values with this particular age, it will be okay. It's not a absolute right way to do it, but it will be more or less okay if we do that. So that's what we're doing. We just created a new age column, and let's just run this thing. And moving forward, now that we have filled the age, the heat map should show that there will be no null values in the age column, and it clearly shows there are no null values in the age column. Now, as part of the pre-processing step, the next thing that we need to do is we'll have to drop the features that we don't need for this training step. Obviously, cabin is something that we are not going to use for this. So we're just dropping the cabin column altogether, as well as, like, we're also doing, if there are, other than these, if there might be some places where we missed the null value, so we are just dropping all the null valued row items completely from the data set. And the next thing that we need to do is, as you can see, that the gender data that we have, it's a categorical variable, right? And if I remember correctly, I was explaining it to you in the last class, in the last discussion, that these are since these are categorical variables, the computer can only understand numerical values. It cannot understand categorical variables. So the thing that we need to do is we need to convert these categorical variables into numerical ones. So what do I mean by that? Let me just use the board for it. So let's say you have in the gender, we have male and female. We have male and female. So one way to convert these into numerical values would be directly give all the male as label 0 and all the female as label 1. But the problem with this kind of labeling is that we are just, because 1 is greater than 0, we are kind of introducing some bias into the model that we're building. So this might not always do well, and this is called label encoding, by the way. Label encoding. So let's say if you have a data set like this, where it says gender, and this is the label encoded, gender label. So if at all it is male, we'll say 0, female it's 1, male 0, female 1, female 1. So the data set will look something, so the updated data set will look something like this. But this essentially is not a very good representation, obviously, because of the bias that we're introducing into the model. So what we do instead is we use something called one-hot encoding to remove this bias from the model. So what one-hot encoding does instead is we take the labels like male and female. Let's say these are the only two possible values of that categorical variable, and we create a representation for it. Let's say a list kind of a representation for it, and based on the index of this list. So this the first value represents, index 0 represents it's male, and index 1 represents female. And if at all a label is male, we will fill the first value. We'll just flip that bit to 1, and we'll put this to 0. And similarly, if it's a female, we'll just put the male bit to 0 and set it to 1. Now, this is what happens like if at all we have only 2 variables. But what if we have like 3 labels? Let's say different types of chocolates. Like we have Reese's, we have Snickers, and let's say we have Hershey's. So let's say this, we have 3 labels. Then automatically what we'll do, we'll convert this into a 3 label list. And so the first one will represent Reese's, the second one will represent Snickers, and third one will represent Hershey's. And for this, let's say the data comes like Reese's, Hershey's, and Snickers. Let's say this is the data that's coming in. We'll create 3 columns. The first column is let's say a flag Reese's, and the second column is flag Hershey's. The third column is flag Snickers. Now, since the first data value, first classification label is Reese's, we'll say Reese's as 1, and we'll put rest all as 0. And since the second value is Hershey's, we'll put here as 1, and the rest all will be zeros. And third is Snickers, so these all will be 0, and this will be 1. So it's just like using, we're just expanding this column of values into row and just flipping the base. So that's what one-hot encoding means in a short manner. And similarly, for this example here, for male and female, what will happen is we are going to create 2 new columns called male flag. Let's call it male flag, and female flag. And we'll have here gender labels. So let's say it has something like female, male, female, male, male. So your since it is female, it will be 1. This will be 0. This is male, so it will be 1. It will be 0. This is female, so it will be 1. This is male. This will be 1. This will be 1. So here 0, 0, 0. So this is how your data frame is going to look like. For if at all you create one-hot encoding. Now, so if you have to do this, you can remember, like, if at all you wanted to do this all by yourself, it is going to take a lot of time, right? So what pandas does, they have this wonderful function called pd dot get dummies. What this essentially will do is it will create all this one hot encoding by the use of this single function. So this is how the final data set is looking like. So here we have the female class and male class and CQS, all the variables that we need. Now, the next thing that we're going to do is we are going to split the training. We were going to split the data set that we have into the X variables and Y variables. So Y is nothing but this TA that we're using. So we are setting that as Titanic data of survived. Yeah, so Y data will be, so we're splitting this data into X and Y variables, and Y values are nothing but your categorical values of survived or not survived, and X data is nothing but your feature vectors. And we're using a Sci-kit learn function called train test split, which will split our training data into X data and Y data. So I can just run this, and it kind of converts your entire X data into a proper numerical, into a numpy array, which could actually be used by by the model that we're going to create in the next step. So now we're coming to the actual training step. So the actual training step in this scenario is very small step. So what we're going to do is we just have three. These are the primary objectives for us in here. We will create a training model, an ML model, and we'll do the training, and we'll see some predictions and some metrics related to it. So for this particular thing, so we're using logistic regression. So we have model.fit. So first we create a model of logistic regression. So what this essentially means is we are just creating an object of logistic regression. To that object of logistic regression, we are giving an input of training data of X values and Y values. And when we said like model.fit, essentially what it's doing is it is taking this initial model that it has, and it's trying to fit the data that we're inputting and creating a function out of it. So that's what this model.fit is doing. Once the model.fit process is done, the next thing that we need to do is model.predict. So how to get the predictions for all the test data. So that's what we're doing. So predictions equals to model.predict. Using the predict function of model will predict all the predictions for that particular model. So I'll just run this. So don't worry about this error. So this is it's just some early turning of it. It's an automatic thing that's done by Sci-kit learn. Okay. So we got some results for the test data. Like you can see whether based upon some parameters, whether they survived or not. Now, the next thing to do is to calculate the metrics, like how well the model is performing. So we'll use majorly two different things. We'll use first one is the classification report, and second thing is a confusion matrix. The classification report is nothing but it just tells us different parameters of a machine learning model. It's just different metrics of a machine learning model. So it's like precision, recall, F1 score. The thing I think you will learn about precision, recall, and F1 score in future classes, but the thing that you just need to care about right now is accuracy. So your accuracy is this much. And we're also creating a confusion matrix. So essentially what confusion matrix is, since this is a two-labeled system, so one is like a positive label and one is like a negative label. Think about the diagonal terms as positive and positive. I'll just write it on the board. So if you talk about confusion matrix, it's primarily used to understand how well the machine learning model is performing. So it is a very simple representation of how well the model is performing, but also it's very powerful. Now in this scenario, we have only two labels. One is 0 and one is 1. On the y-axis, let's take these two values, and on the x-axis also we'll take these two values, 0 and 1. Now, so this is the actual, and this is the predicted. Now, if actual is 0 and predicted is 0, then so essentially what we'll do is, like, let's say we created this matrix of this sort, and we'll go through each and every value that this the y. So let's say these y values are the original values. Let's say it is 0, 0, original predicted value 0, 1, 1, 0, and y predicted, the values of predicted y by the model will be like, let's say 0, 0, and instead of 1, this predicted as 0, and instead of this 1, this, let's say, predicted 1 probably, and let's say this predicted as 1. So if at all you take this kind of an example, it's just fill, like it'll go to the first thing and it'll say, oh, it actually is 0 and the predicted is also 0. So it will just update this to 1, and actually is 0 and again it is 0. So it will just update it to value to 2. And it will go to the third row. Actual is 1, but predicted is 0. So actual is 1, but predicted is 0. So then it'll come here and it will increase this value to 1. So this is a false positive that it predicted. Now next thing is actual is 0, actual is 1, and it predicted 1, so it will be 1. And actually is 0, but it predicted 1. So actually is 0, but it predicted 1. So this will become. So this is essentially what a confusion matrix is. So you can simply say this is like 0, 0. This is 0, 1. This is 1, 0, and this is 1, 1 of your labels. Like based on this, we'll have to fill the total number of examples that are there. So this is what is called a confusion matrix. Now this is all good. Now the next thing that we're going to talk about is feed-forward neural network. So to give you an intuition about the feed-forward neural networks, I'll just explain it with a simple example. So essentially, in logistic regression, what we are doing is we have a single object, which essentially takes in all the parameters. Let's say these are x1, x2, and x3, and it will give out you a variable whether it can be a 0 or 1, right? And this is, let's say, our model. Now, now basically what's happening in here is we have multiple different types of inputs, and we are giving it to the model, and the model is giving 0 and 1. And there is only one learner in this in this system, and that is this single model. So essentially, what this model, as I said in that in the previous discussion, using that logistic function, it's able to predict whether this value is 0 or 1. But a lot of people, what they thought is like, why should we just have a single learner? So why can't we have multiple learners so that the system could perform better? So instead of having one learner, if we expand the problem to multiple learners, will it work better? So that's where the feed-forward neural networks came into picture. So essentially, what we are trying to do in feed-forward neural network is we'll have inputs like, let's say, this is x1, x2, x3, and now this is let's say this is the input layer. Now we will give it to 2 learners in middle, or let's say 3 learners, and all of these will be connected to all of these. And let's say there is one more and the final output layer, and this is what is giving us whether it is 0 or 1. So essentially, previously we have only one learner, and now we're just expanding it to many learners. So this is called a hidden layer, and each processing unit in this is called a neuron. So this is essentially a word, what a feed forward neural or a general concept of neural network in a very niche manner, saying this is what pictorial representation of what's happening. To actually kind of get some sense into it, think of a classification problem of whether you're trying to predict a cat in an image. So essentially what this part in here will do is, let's say this neuron predicts the ears of the cat, like this, like this, like this. And this part creates the eyes of the cat, predicts the eyes of the cat. And this part predicts the face of the cat, like the nose or something. So when you give an image, each of will have like different learning objective, and they'll learn those particular things. And finally, you'll club all these eyes, ears, and nose, and we'll combine all these features and say, this is a cat. Think of it in that way. Even though I said in an arbitrary manner that this will be zeros, it'll predict eyes, it'll be predicting ears. It's not actually very easy to figure out what each neuron is going to learn when you are giving the inputs. That itself is a very good research problem to solve. Yeah, so this is the intuition about neural network. So essentially what we're doing is we're just taking one single learner and we are just expanding it to multiple learners. Now we'll use the same thing for feed-forward neural network, the same data. And so the one that does the feed-forward neural is MLP classifier. So for just the simplicity purposes, I'm doing a random state of 42, and hidden layers are like 2, 12, and 3, and maximum iterations as 500. I can change this parameters. So all these values are called hyperparameters. So what hyperparameters are is like, so these are the kind of parameters that you need to set. So there are 2 types of parameters. One are your weights of the model. So these are the parameters that are automatically set by your machine learning models. And second one are hyperparameters. Hyperparameters are the ones that you should give as an input. So what, like for example, y equals to theta naught plus theta 1 x. Let's say this is your model that you're trying to predict. Your theta naught and theta 1 are your general parameters. And what will be your hyperparameter? In linear regression, we have alpha, like W nu equals to W old minus alpha into dou E by dou W. So this alpha is a parameter, is a hyperparameter that we should. So there are some indirectly the parameters that we set, which in turn affects the overall model. So that those are what called hyperparameters. In this, in here, the other hyperparameters are the number of neurons you have in the intermediate layer, and what is the random state that you. So all these are sort of hyperparameters which will in one or the other way affect your model. So let me just run this. So here I'm just using MLP.fit. So it's the same thing as the previous one. There's not much difference, and we'll see the classification report. So here we can see that we only got 68% accuracy. That's because my hyperparameters may not be as good as. So if I change the hyperparameters, the whole scene also will change. And how to find the optimal hyperparameter for a specific problem. So that's where the hyperparameter tuning comes into picture, that you will learn in the next segment. Now coming to the last part of the discussion. So we are here to learn about Newton's method. So what Newton's method, and a simple, in a very, I think I have a picture which could show you what a Newton's method is in a very simple manner. So essentially in gradient descent, what, or I'll just use the board. Essentially in a gradient descent example, as I've told before, let's say you have a function and you are trying to find the minima. You're trying to find the minima where this weight will become, which values of W will ensure the error is the minimum. So let's say you're starting at this arbitrary point. Now in gradient descent, you take small steps of delta W towards the minimum, but what will happen is it will take a lot of time to reach to minimum. So instead, there is another way. So people thought, like, why not I just travel through the gradient and see where it touches x-axis, and you take that as the new weight, and again repeat the same process. Again, you do this is exactly what, let's say it's going like this. It is hitting it here. Then again you take from here. So you take this weight. Essentially, what's happening is, like, you are one or the other way trying to converge into the middle point. So that is so instead of taking a small step delta W, you're actually taking a big step of this value. So this is nothing but your Newton's method, and there are already formulas given, like how you can figure that thing out. So if you have any questions, please feel free to come and ask in the office hours. Now let's discuss about homework 2 quickly. Okay, so in homework 2, you were given a problem to. So there is this data set called dry beans dataset. You are asked to build a feed-forward neural network, and so as I said, in the feed-forward neural network, there are certain steps. First thing is to do data pre-processing. Then you do the training and testing on the neural network. And we also given the parameters that you should, hyperparameters that you could use for this particular thing, and also given how much ratio that you should split your training and testing into. And the second step is to do k-fold cross validation, and I think it should, like, it is as similar as I think you'll learn it in your next discussion, how to do k-fold cross validation and hyperparameter tuning. So this is primarily what you need to do in homework 2. So you take this data set, do some pre-processing, and then build a MLP classifier, which is nothing but your feed-forward neural network. In the pre-processing step, you might have to do the min-max scalar normalization, or you have to convert it into, if at all there are any categorical variables, you have to convert them into one-hot encoding labels. Then in your second section, you have to do the k-fold cross validation, and you need to in the third step, you're doing a hyperparameter tuning. So I think you'll learn about k-fold cross validation, but to give you a simple idea of what k-fold cross validation is, you're splitting your data set into, let's say in here, 90% and 10%. Essentially what you will do is you will rotate this 10% test across the data and try to figure out the MSU value and optimize the model. So that's what k-fold cross validation means. Yeah, that's it. Thank you. Have a good day.